Mathematical physics is built upon a fault line between the continuous and the discrete. Classical mechanics and general relativity describe a universe of smooth dynamical evolution, where space and time bend without fracturing. Quantum mechanics introduces a different requirement: discrete jumps, localized states, and countable observables. This division creates the island view paradigm. It treats these two domains as primitive, isolated states of being that naturally resist one another. Standard theoretical approaches attempt to build mathematical bridges between these territories after the fact, a process that frequently results in intractable infinities. Philip Lillian's framework proposes that this is a foundational misframing. It suggests that neither the discrete nor the continuous is a primitive state. Reconciling these domains involves identifying a deeper ontological ground from which both originate. This tension traces back to the ancient separation of discrete arithmetic from continuous geometry. Modern physics inherited this split through general relativity's reliance on the continuous spacetime manifold. Max Planck's discovery of the quantum reintroduced discrete constraints, showing that energy is exchanged in specific packets. Niels Bohr applied this to the atom, describing electron orbits as a series of isolated steps rather than a continuous flow. Erwin Schrödinger's wave mechanics highlighted wave-particle duality, where continuity and discreteness appear to occupy the same space. Werner Heisenberg's matrix mechanics further demonstrated that physical observables arrive in discrete, countable packets. These discoveries have long been treated as competing first principles. This framework suggests they are instead partial views of the same underlying generative process. The framework begins with generative closure, or C. This is a productive principle. It drives a regime to become internally stable, bounded, and reproducible. It functions as the active generator of form. Closure acts upon the coherent continuum, denoted as K. In this model, K is intrinsically structured by relations and coherent variation. It replaces the concept of an undifferentiated, featureless background. This establishes a relationally structured medium subjected to a stabilizing principle, providing the conditions for both particles and fields to emerge. When generative closure acts on the coherent continuum, it produces the primary regime of reality, the quantized continuum, or Q. This regime serves as a deeper ground, sustaining both continuous extension and stabilized limits within a single generative field. Quantization functions as a structural event. It is an internal manifestation of stability within the continuum. A state, M, is quantized when it becomes closure-stabilized, yielding a persistent form, M star. This stabilization occurs from within the continuum. The persistent unit represents a region where the continuum's internal architecture has achieved a stable configuration. A quantized value, or particle, is a closure signature, the evidence of the continuum's own generative architecture. This architecture results in a stratified ontology driven by graded closure. Different intensities of closure produce different structural limits. The geometric sector, or G, is the expression of large-scale, broad relational coherence. This sector provides the continuous relational order mapped by general relativity. The spectral sector, or S, is the expression of highly localized, sharp stabilization. This sector yields the discrete states and observables encountered in quantum theory. The macro and micro worlds appear as differentiated regimes of the same underlying field. Solving quantum gravity involves determining the coupled closure dynamics of Q. The first term accounts for the geometric closure contribution, representing continuous gravitational order. The second term accounts for the spectral closure contribution, representing quantized stability. The interaction term ensures mutual consistency between these manifestations. Because geometric order and spectral stability emerge coupled from the start, unification rests on this internal interaction term. In this theoretical framework, a particle is a highly localized field closure. A field is a broadly distributed continuous closure regime. Attempts to quantize classical geometry, or geometrize a discrete quantum substrate, start from derivative limits rather than the generative ground. Progress requires mapping the architecture beneath the sectors, treating reality as a series of stratified regimes. The discrete and continuous function as dual expressions of one single generative ground. This framework replaces the conflict of quantum gravity with unified closure dynamics.